I'll be knowing how many people are joined.
I'm still waiting, sir, for the live to go on.
Sir, you're live now. You can start the session.
Okay. Good evening to all of you. Welcome to the live session on aqueous corrosion and control. I do hope that the lectures have been very useful to you. And this session is meant to clarify any questions that you have in mind. Please go ahead and send your questions through the chat box, right? And we will address the questions one after another. Please, you're welcome. Is there any possibility to know how many people have joined?
There are two others, I think.
Okay. Yeah, please feel free to ask any questions and doubts about the lectures that you have been listening to. And also, if you have any doubts about the assignments, that also you can ask questions. So we'll be happy to answer. So we'll wait for about a couple of minutes. There are no questions so far. We'll wait for about a minute or two. If there are no questions, I would suggest that we can close this interactive sessions. So please send your questions if you have any. Well, I don't see any questions from anyone. And so we can now close our online interactive sessions.
Should we close now, Omkar, or?
Yeah, I think we can close down actually. Yeah. So thank you guys. If there are no questions, we close it. I do hope that the lectures were useful. Also, feel free to send your questions even offline. We will be happy to answer your questions. Thank you. Thanks all of you for arranging this online session. And we'll end the session today. Thank you.
Sir, we have a question now.
Yeah, please.
It's from Basim Imam. So he's asking, kindly explain on anodic polarization.
Kindly explain on the anodic polarization. Well, I think you know what is meant by polarization, right? Any deviation from the equilibrium condition is called polarization. For example, suppose I immerse, say, copper in 1 molar copper sulfate solution. It will exhibit a potential which is equal to standard potentials. And then you apply a potential relatively positive. What I mean by that? Suppose if the potential of the copper sulfate is, let's say, plus 0.334 volts. If you raise the potential to, let's say, plus 0.2 volts, then what happens? You're applying a over voltage which is equal to positive. What is the over voltage? The over voltage is equal to E applied minus E equilibrium condition. So in this case, E applied is plus 0.2. Okay, sorry. Yeah, I'm very sorry about it. You applied, if you apply from 0.334 volts, you raise it to, let's say, plus 0.5 volt. Then you are applying a over voltage, which is positive in nature. That means the applied voltage is 0.5 and the equilibrium potential is 0.334. So the difference is positive. And so the metal is now polarized anodically. You're raising the potentials. In which case, the equilibrium shift towards an oxidation. The metal is getting oxidized. And that is called as the anodic polarization. And on the other hand, if you are lower the potential, let's say from 0.334 volts to, let's say, plus 0.1 volt, then the E applied minus E equilibrium is equal to negative, which means there is going to be cathodic reaction. It moves towards the cathodic reaction. That means copper 2 plus will combine with the 2 electron and form copper. So that is a cathodic reaction. On the other hand, if you move from, let's say, 0.334 volts to, let's say, 0.5 volts, then what happens? Copper will get oxidized as copper 2 plus 2 electrons. So you get a current, which is called anodic current. Now, this is about equilibrium potentials. You can also have anodic polarization with respect to the corrosion potential. For example, suppose you immerse, let's say, a stainless steel in seawater. If the corrosion potential is, let's say, about minus 0.3 volts with respect to, say, saturated calcium electrode. Please notice, always the potential is referred with respect to a reference electrode. So, if you are going from, let's say, minus 0.3 volts with respect to saturated calcium electrode, you move towards, let's say, plus 0.1 volt. Then what happens? The metal starts getting oxidized more. That means the current will start increasing, possibly, as you start polarizing on the positive direction. Now, when the polarization occurs, suppose it's a stainless steel, it is possible that the anodic polarization can lead to passivation, which means the current also can get reduced. Okay, because as you start polarizing anodically more and more, even though the over voltage can be more positive, when there is a passivation, the current density can come down. So anodic polarization in simple terms means the over voltage is positive. And if the over voltage is negative, it's a cathodic polarization. Current increases or decreases, that all depends upon the kinetics of the reaction. I hope I made the point clear. If you still have the doubt, you please do send me the question again.
Thank you for answering his question. He has also added, is it used in acid tanks only? The anodic polarization.
Okay. So this is called as anodic protection. Okay, this is called as anodic protection. Okay, the anodic protection is used on systems where the metal starts passivation. Okay, that means you're right. In sulfuric acid, for example, if it is a concentrated sulfuric acid, the steel starts showing passivation at higher anodic potentials. Whereas the corrosion potential is lower, so you need to raise the potential to the positive direction so that you are going to the passive region, right? So you need to go to the passive region from corrosion potential. So you are polarizing anodically. And so the metal is taken to passive region, passive potentials. And so there's a passive current density. That passive current density is equal to corrosion current density. Yes, this is called as anodic protection. Anodic protection is happening only in limited cases. In this case, for example, steel in sulfuric acid, stainless steel in sulfuric acid. Some metals also passivate in phosphoric acid. Okay, so passivation is one of the very much requirement for anodic protection of metals. Yeah, is there any other questions?
No, sir. No further questions.
Okay.
Yeah, he has also added one more.
Yeah.
As per mixed potential theory, I cathode and I anode are equal at intersection, and current is I core, which indicates corrosion. But then at intersection, metal have potential E core. When whole material is a single potential, then what is the driving force for the corrosion?
Yeah. Okay. I mean, it's a very, very interesting question. Now, please understand, on the metal that you talk about, both the reactions occur. Okay. What are both the reactions occurring? One is an oxidation reaction. What is that oxidation reaction? Let us take the iron. The oxidation of iron is equal to Fe, giving rise to Fe2 plus 2 electrons, right? Isn't it? Now that is oxidation. What is reduction reaction? Assume it is an acid, right? The reduction reaction is H plus 2 electron gives you one hydrogen molecule, right? So this is the cathodic reaction. Please look at the cathodic reaction is different from the anodic reaction. What does it mean? H plus is getting reduced as hydrogen. Iron is getting oxidized as Fe2 plus. Now, where is the driving force? Now, E core is the potential, right? Now, look at the E core. The E core potential has an over voltage. What is over voltage? Over voltage is the difference between the applied potential and the equilibrium potential. For iron to get oxidized, what is equilibrium potential for iron? For iron equilibrium potential, assume that iron is in 1 molar Fe2 plus, for example. The iron potential is going to be something like minus 0.44. So minus 0.44 is the value for iron. Now the E core is going to be positive. E core is positive to the equilibrium potential for iron. E core is negative in relation to the hydrogen equilibrium. Please look at. So for hydrogen equilibrium, E core is negative. So there is a reduction reaction. E core is positive in relation to ion equilibrium. So it is an oxidation. So it might look that the potential is the same, but the driving force for the two reactions are different because you're starting from equilibrium. there are two independent equilibria we started with. So when there's a corrosion, there's one oxidation that is not related to ion equilibrium or ion, no. The ion oxidation is related to ion equilibrium. Hydrogen reduction is related to the H plus equilibrium. So it is not equilibrium condition at all. Okay. So there is a driving force given by the over voltage, and over voltage for both the reactions are different. Okay. Because equilibrium potential for both are different, and ECOR is applied potentials. So you can able to now visualize the mixed potential theory, how it happens. Okay. So you apply the concept eta is equal to E applied minus E equilibrium, and E equilibrium is different for both of them, but E applied is same, ECOR is same. So you find the sign for eta is going to be different for both of them. And so one is getting oxidized, other is getting reduced. I hope this point is clear to you. If you still have the doubt, please let me know. Thank you very much for the good question.
Thank you, sir. There is one more question from Joydeep.
Yeah.
Sir, will corrosion happen in pure water, no dissolved oxygen, or any impurities having pH 7 at ambient condition?
Thank you very much. I think Jaideep, right? Okay. For the again good question. Now, pure water, the solubility product is pure water, and the pH, let's say, is 7. The solubility, I mean, the K value, okay, K value, or KW, okay, is 10 power minus 14. So the concentration of H plus ion equal to 10 power minus 7. The constant, or activity is minus 7. And similarly, for hydroxide, it is again 10 power minus 7. So the activity of H plus ions in water of pH 7 is very low. So does it mean that it will be corrosion? Yes, that can be corrosion. But the activity is very low. The corrosion of steel or iron in water is very low due to H plus. Okay. Then what else can happen? You can also have a dissolved oxygen content, right? The dissolved oxygen content can be in the range of 6 to 8 ppm, depending on the temperature and other salts. Okay. Now the dissolved oxygen, what happens? The oxygen can, as in water, can combine with the electron, that is oxygen plus water plus electron gives you hydroxide. So there is another cathodic reaction taking place, and that cathodic reaction is dominant. So when iron dissolves and gives 2 electrons for 1 atom, these electrons are consumed by the oxygen present in the water and forming hydroxide. So you have 2 parallel reactions occurring. I mean, cathodic reactions. One is the oxygen reduction reaction. Other is your H plus reduction. And H plus reduction is very, very slow. And so predominantly it is the oxygen, dissolved oxygen that happens. So if you remove all the oxygen content in the water, then you find that the oxidation of iron is very, very low, actually. Okay, I hope that question is clear to you. Any other questions?
Yes, sir. Vasif has further asked, in case of anodic protection, although I passive is low, but high current or polarization is required to cross the I critical, is it cost effective? Or can we apply coating to reduce current requirement in anodic protection, as in the case of cathodic protection?
Yeah, it's a good question. You have to rise the potential, very good. Of course, there's I critical you have. That means the potential means it crosses. So initially, the metal will dissolve at a higher rate because I critical is significantly higher, right? So initially, when rise the potential, you'll find the metal will corrode at a higher rate. But then the moment you go into passive region, the metal will corrode at the rate which is equal to passive current density. Yeah, it's very correct. Initially, it will corrode, but moment you cross the passive potential and you keep the metal in the passive region, the corrosion rate becomes very low. Actually, so but then you can't give. See, the moment you give a paint or something like that, the metal will not passivate, right? Because you are applying anodic thing now. Okay, the passivation will occur only on the metal surface. So passivity is not possible when you apply a paint coating. In the case of cathodic protection, you apply a paint coating because it reduces the current demand for that actually. Only through that pores, the defects in the coating, the current is flowing, so the amount of current required for cathodic protection becomes very less. Okay, so anodic protection, invariably, you find no coating is applied. Anodic protection means passivation, and passivation has to occur only on the metal surface. Thank you very much for a very provoking question. Very nice question. Thank you.
He has also added, are such coatings prevalent in industry?
No, anodic, there is no coatings applied for anodic protection. If you apply, for example, suppose you take a sulfuric acid tank, okay, you simply apply a backlight coating, right? Okay, you can do that, okay? So I don't think you do, it doesn't serve the purpose of applying anodic protection and the coating. Because if for example, see, if you, the difference is that when you apply, see, the difference between the cathodic protection and anodic protection is, cathodic protection is thermodynamically a stable state. When you apply cathode protection, current will always decrease. In the anodic protection, the current will decrease provided the metal passivates. Assume that you have a metal which is anodically protected and somebody makes a deep scratch, you'll find that the corrosion will start occurring at a much higher rate because the driving force, the war voltage is more. The driving force is very high. The corrosion will occur at a very high rate. So passivation is the key, and you don't apply any paint coatings to promote the anodic protection of metals.
Thank you, sir. There's one more question from Joydeep.
Yeah.
Sir, why in copper aluminum alloys having 20% aluminum selective leaching occurs, although aluminum can passivate, which is the case in stainless steels where chromium passivates and protects it?
Yeah, it's another good question. In copper aluminum alloys, first of all, the selective leaching occurs when there is a huge driving force between the elements that are added. Copper and aluminum are added like this. The aluminum, if aluminum does not passivate, then the corrosion potential of aluminum is very, very, very negative. And copper has a positive potential. And so aluminum will start dissolving from the alloy, right? If by some reason, if you form a nice passivation, then it forms a barrier for the overall corrosion of the system. Okay, suppose you form a thick, nice aluminum oxide, okay, I think that becomes a barrier for that. But by some reason the oxide is broken, then you'll find that aluminum will start dissolving selectively. Okay, so the selective dissolution of the active metal is possible once it reaches a critical concentration. Say, for example, copper zinc, the critical concentration is 15% of zinc. Within the 15% of zinc, you don't get selective dissolution. If you increase the zinc beyond that, there is selective dissolution takes place. So each metal, similarly, if you take copper nickel, for example, then you can add more nickel. Okay, still the selective dissolution may be not that severe compared to copper zinc. That depends upon the potential difference between the elements that you are considering actually, right? As the potential difference more and more, you have selective dissolution becomes more and more. And also If also depends on the environment. The environment is not very severe, it's a little milder, for example, then the overall corrosion rate decreases, selective dissolution also decreases actually. Okay, so I hope this answers your questions. If not, please do let me know. I will clarify further.
Thank you, sir.
you.
There is one more from Vasif. He's asking, kindly share some insight on EA's application to corrosion study.
Can you repeat the question, please?
Kindly share some insight on electrochemical impedance spectroscopy application to corrosion study.
Oh, well, it's a very big question, huh? Okay. See, first of all, let me try to clarify certain things about application of the technique for corrosion studies. Suppose somebody really wants to know what is the corrosion rate, just the corrosion rate, okay? Mere weight loss measurements is sufficient. It is simple, direct, straightforward, no assumptions are involved. Then why do you need to go for electrochemical studies? The reasons are as follows. Suppose somebody gives you, let's get titanium alloy or an alloy which undergoes very low corrosion rate, and you might have to wait for 1 year to see the appreciable loss in corrosion rate. It takes time to dissolve, right? Then weight loss measurement becomes a problem. It takes longer time to do. Whereas the electrochemical technique will tell you in about 2 hours, maybe simple polarization curve tells you what is the ICOR value. From there, you can determine the corrosion rate. But even more important in using electrochemical polarization curve is to understand the mechanism of that. Okay, you are now not only reporting what is the corrosion rate of the metal, you are trying to understand why the corrosion occurs and try to understand how the corrosion can be mitigated using the polarization curves. So, understanding mechanism, you need electrochemical technique. Now, okay, suppose I want to use, let's say, polarization technique. It's a DC polarization technique. Then I can use Stafford extrapolation and find out the ICOR values. Or I can look at the pitting potentials. I can look at the film breakdown or look at the passive cut density, look at the Aqueous corrosion, all kind of things you can do, form a passive film, analyze the composition of that, all kind of work that one can do with the polarization studies. Now, suppose if I need to find out the rate of corrosion or change in the rate of corrosion of the metal with respect to time, then your Tafel extrapolation does not work. Then you go to linear polarization technique. But the linear polarization technique has some limitation. If the solution has high resistance, the solution resistance itself becomes very high. You can't separate the solution resistance from the resistance or polarization resistance offered by the system. So then what do? You go to electrochemical impedance spectroscopy. Now, electrochemical impedance spectroscopy is a non-destructive technique similar to LPR, linear polarization technique. So non-destructive technique can be used in order to find out the change in the corrosion rate with respect to time. The simple way, okay? But suppose I want to go a little bit more in details. For example, a metal is getting passivated, right? Now, if metal is getting passivated and start getting pitting, for example, then you can do what is called as a time-resolved electrochemical phenomena. Now, there is some pitting taking place. I want to know how the pitting takes place with respect to time, for example. Okay. Or if I want to know a passivation, so what is the resistance offered by the passive film? I can able to do that. Or if there are corrosion processes that involves a diffusion phenomena, I can able to look at I separate out the diffusion from the charge transfer taking place. Or if, for example, I have in fact, look at the paint coatings. Paint coating, you can't do polarization experiment at all, right? In paint coatings, suppose you want to know, what is the resistance offered by the film. No Tafel possible, Tafel equation is not applicable at all, okay? Now you use impedance spectroscopy to find out the film resistance. Now again, in the film resistance, suppose you want to find out what is the degradation taking place, what is the water absorption taking place in the film, for example. Okay, so you can even determine the water content of the passive films. So like that, you need to first of all frame the question and then choose the technique. Okay, I want to know this particular one. Okay, then what is the right technique to do that? Okay, is weight loss measurement sufficient? Is polarization curves sufficient? Or impedance is sufficient? Okay, I've done impedance, polarization things, even but they are not sufficient. Still, I have to go for applying what is called as X-ray photoelectron spectroscopy to find out the film things. So you should pose the question differently as to what is that I wanted to know and which is the right technique for me to use it. And from that point of view, yes, EAS is a very valuable technique, but please mind you that EAS is more difficult because you need to have an superior knowledge. What does it mean? I may have, if I plot an aqueous plot of imaginary impedance versus real impedance, I may get a semicircle, whatever it is. I may get one semicircle that does not say anything. Is a passive film or no passive film, or is it a coating? All by getting same thing and all like that, right? But if I only know the metal is undergoing passivation, then I'll try to fit that particular data to passive film. Otherwise, if I want to use simply a metal which is not passivating, I cannot fit the data for a passive film. So I need to have an superior information about what happens at all, or it has to be validated, for example. Okay, so using impedance spectroscopy means you need to have some idea about it and try to validate it and try to find out that is working at all. Simply, it is not a direct technique like what you do in the case of a simple DC polarization technique. I have a tapered slope. I just get these things all possible, but here it is not possible unless you know what is going on at the interface. Yeah. Sometimes, sometimes of course you can have a nice time resolved, two semicircles are appearing, all these are possible, but not always actually you get it. Yeah. Thank you. If you have any questions on that, we can clarify more. Yeah.
Thank you, sir.
Thank you.
One more question is, kindly guide in transpassive region, the current increase due to water electrolysis or due to the metal dissolution?
Yeah, it's very nice question. It's a fantastic question actually. Now you have to look at now the Pourbaix diagram, or you look at the thermodynamics of the reactions. For example, assume that I am carrying out an experiment in sulfuric acid, okay, and a stainless steel. Now the transpassive dissolution occurs, let's say it's about 1.4, something like that. Assume that it happens at plus 1.4, okay, with respect to, say, saturated calcium electrode, for example. Now, you look at that particular potentials and look at the equilibrium related to oxygen there. You have oxygen plus electron plus 4H plus gives you 2 water, right? So that is another equilibrium that you have, right? Now, for a standard state, that equilibrium has a potential which is plus 1.2 volts with respect to standard hydrogen electrode, okay? Now, we are talking about plus 1.4 volts with respect to saturated calcium electrode. You find out what happens with respect to standard hydrogen electrode. If it is beyond plus 1.23, very likely that you have oxygen evolution taking place, right? So, oxygen evolution, you can first of all predict using the thermodynamic concept. Okay, of course, assume what is the oxygen solubility. All this, of course, you would fit in the Nernst equation. You do that. But of course, then it is over voltage. It may not happen immediately. At equilibrium potential, you have to deviate from that. But once you deviate from here, then you have oxygen can evolve. Water gets split, and the oxygen can evolve. So one way to look at it is that you see the electrode surface, there can be oxygen evolution taking place. That's one way of looking at it. If you are a little more, But somebody will ask, oh, can there be hydrogen evolution? It cannot be hydrogen evolution, isn't it? At that particular potential, hydrogen cannot evolve at all, right? It has to be only the oxygen evolution taking place. Now, if you have still a problem, little bit, of course, you can use thermodynamic concept, or you can, if you have some good equipment and all, you can take the mass spectroscopy, you can analyze and all like this. Now, other way of looking at is, yes, there can be oxygen evolution reaction. There can be, of course, metal oxidation take place. After all, it can happen, right? So how do you resolve this? The first attempt is to see whether there are any gas evolution taking place. The second is, at the transpassive potential, we hold the sample at that particular potential, take the solution out, and then analyze the amount of metal ions present here, right? Now we can look at the Coulombic things, right? You know the amount of current that is flowing, current density. You know the amount of metal that is going to dissolve in solution. You can able to say that, yes, this current now is due to metal dissolution. You can hold it at a passive region and find out the metal dissolution, for example. And you can take it to transpassive region, take the solution out, and then analyze it. If you say that, yeah, metal dissolution is more there, yes, the transpassive dissolution involves metal dissolution taking place at all, right? Otherwise, it can be purely oxygen evolution reaction. So that means you need to go step by step and analyze what really happens. This is what I would normally do. I take it thermodynamically things and look at all the possibilities, start eliminating one after another, and come to the conclusion what is the kind of reaction that occurring on the surface. Yeah, thank you. Very nice questions.
So adding to that, if it is due to water electrolysis, then why metal corrodes in this region?
Yeah, metal is over voltage, right? I mean, both the driving force is sufficient for the metal to dissolve, right? Suppose I assume that I only iron, right? For argument's sake, you only have iron there. You taken the potential of the iron to transpassive region, but that over voltage is what? Look at the equilibrium potential of iron and the applied potential. What is the transpassive potential? It is applied potential, right? That applied potential is quite positive compared to the equilibrium potential, right? It's positive, over voltage is positive, so metal will dissolve. How much metal dissolves? How much is metal, current is due to metal dissolution? How much is due to oxygen reaction? That one has to determine from that, right? So the over voltage is still positive. That is what called anodic polarization. Anodic means metal has a tendency to dissolve. Passivation makes it less dissolution. It never says no metal will dissolve at all, right? It dissolves. And the transpassive dissolution means assume that film is getting dissolved. No film is there. So yeah, metal can dissolve also. Okay.
Thank you, sir.
Okay. Thank you.
There is another question from another person, another learner. Sir, can pitting occur even if the potential is in the passive, or does it occur only when it passes the transpassive region?
It's a good question. See, let me put this. The transpassive potential is a general description of the potential above which current is increasing. Understood? When I say transpassive potential, it is the description of the potential above which there is an apparent increase in the current density in the polarization curve. Now, what is that current due to? The increase in current density can be due to oxygen evolution reaction. Metal dissolution can happen uniformly possible, or it can be pitting taking place. Pitting also can take place. Now, all possibilities are existing now. Okay, suppose now you want to ask a question that is, okay, is the transpassive dissolution taking place uniformly or pitting? The one way to look at is hold the sample of the transpassive region and then for some time and take the sample out. Of course, switch off your potential stat, take the sample out, clean them, dry it, take the microscope and see there are pits. If there are pits are there, then of course, then you say very clearly, yeah, that particular potential pitting takes place. Now, it's very interesting to see at what potential pitting takes place. Now, if you go by simply the polarization curve, okay, I think the pit is where the pit starts initiating, okay? So you find that you just above the pit actually, you stop and see them in the microscope and see the pit. Of course, you have to allow more time because sometimes the incipient pitting, very small, sub-micron level pitting, you won't be able to see. You allow for more time. Okay, you can see this now. The other way of looking at whether it is a transpassive thing or a pitting is you do a reverse cyclic, right? You do a reverse cyclic. I think when there's a pitting taking place, you see that the hysteresis is going to be a negative hysteresis. That is, the reverse curve will have a lower current density as compared to the forward curve. So the pitting, the reverse current will be always higher than the forward current. Why? The pits remain active dissolution. So you find that more current is coming in the pitted area, okay, and so the reverse curve will be always showing a positive hysteresis loop. That is another way of looking at whether it is a transpassive dissolution simply, or is pitting really, or due to oxygen evolution reaction. That also you can do that actually. Okay, any more questions?
Yes, sir. How can we interpret mixed potential theory for metal lying above hydrogen? Does ICOR holds valid for such cases? Metal will act as an anode with respect to the hydrogen and cathode with, he's saying with respect to the hydrogen in such cases.
Can you please repeat the question again?
So he's asking basically how can we interpret mixed potential theory for metal lying above the hydrogen? So does ICOR holds valid for such cases?
Yeah, okay. If I understand correctly, that is called an equilibrium potential for hydrogen. Okay. If the equilibrium potential for hydrogen is below the equilibrium potential for the metal, okay, if I understand correctly, right? If you have an equilibrium potential for hydrogen is below the equilibrium potential for the metal, then we call that metal as a noble, right? What does it mean? Isn't it? That's where you look at the standard potentials. There is 0, 0, and below that you have active metals, and above that you have noble metals. So what is the meaning of that? The meaning of that is very simple. Suppose, let me take this one. Suppose you take, say, a platinum, and in that you take a copper sulfate solution in platinum, nothing happens, nothing happens. Suppose you bubble hydrogen gas now, okay? What happens? The hydrogen gets oxidized, and copper 2+ will get reduced and form copper, okay? So what does it mean? The potential goes hydrogen above this, okay? That's what happens. Now, so this is about without external current, okay? Okay? So, to say this way, if the equilibrium potential of hydrogen is higher than the equilibrium potential of metal, then okay, if the equilibrium potential of hydrogen is higher than that of the metal corrodes because the potential starts moving up. It's other way around. Now hydrogen gets oxidized, the metal gets reduced. Now, I don't know whether your question is slightly different. For example, in mixed potential theory, if I am moving the anodic curve above the hydrogen, okay, okay, then hydrogen also gets oxidized. You are right? Oxidized, right? Okay. Now the question is that what is getting reduced? The question that may be asking at all, right? Okay, is that your question? I suppose. Suppose in a polarization curve, the mixed potential theory, you have ECAR. That is above, you have equilibrium potential of hydrogen. The curve goes on going up above the equilibrium potential of hydrogen. If the polarization curve goes up, what happened to metal? The metal will get oxidized because the over voltage for the metal is still positive. Now the over voltage for hydrogen also positive. The hydrogen also gets oxidized. Metal also gets oxidized. Okay. Then what is getting reduced? Because in that case, you're also making the counter electrode. The counter electrode is what is made as a cathode. The cathodic reaction is now occurring on the counter electrode. That may be some other reaction, some other cathode reaction takes place. Okay, it can be it can be some other because the electron goes right. It can be an oxygen can get electrons and get reduced. So you are now what you're doing is you are shifting all the cathode reaction on this surface into the counter electrode. So the counter electrode would have a cathode reaction. What does it mean? The total amount of hydrogen oxidation, the total amount of metal oxidation, that total current should be equal to the cathodic current occurring on the counter electrode. Okay, that has to happen. Without that, the reaction will not happen. Okay, I hope you understood the point which I am trying to say. If you still have doubt, please let me know.
So to add on to that, he has asked whether do we have mixed potential chart for these noble metals, provided we don't have any ions of these metals in solution.
Okay, see, okay, let me just put this. Mixed potential diagram is not unique at all, you know. The mixed potential diagram, it depends upon the system. If you have 2 or 3 more equilibrium that you have, equilibria you're going to have, now you find that equilibria will start shifting, based on the potentials that you're going to have. Now, I don't know whether you're talking about, platinum, for example. Okay, suppose what happens with platinum? Suppose I have platinum in the solution, for example. Why are you always using the kinetic curve for hydrogen, kinetic curve for iron only? You are not using the kinetic curve for platinum. Is that your question? Suppose, right? In the events diagram, we normally put hydrogen is happening at the platinum, something like that. You put iron, but what is happening to platinum, right? See, the platinum, the question of platinum is simple. The platinum is a noble, right? So, if the platinum has to dissolve, the potential has to go above the equilibrium potential of platinum. So, it has to be so high. At that case, what happens? Hydrogen will oxidize, metal also get oxidized, above that platinum also get oxidized. Now, why is that we are not showing the reduction reaction for platinum? We are not showing because solution does not have platinum. Okay, if solution has a platinum, what would happen is you'll find the cathodic reaction will be hydrogen evolution reaction, and along with that, the cathode reaction will be platinum 3 plus, 3 electrons gives you platinum. That also will happen, right? So that is why some cases we have used mixed potential theory where you have Fe3 plus added, right? Fe3 plus also comes like this. So normally when you say platinum, we don't add platinum ions because platinum ions are not there at all, right? Suppose you add it, yeah, platinum ions will get reduced and also give current actually. Okay. Yeah, your question, that is what your question is, yeah, it's a good question. Yeah, it could happen. Any other questions?
Yes, sir, we have one more from Joydeep. He is asking, there are 2 containers having 2 steel nails in each one of them, containing in water. One is pumped with nitrogen and the other with oxygen, which would undergo higher corrosion if they are connected with a wire, and why it happens.
Yeah, can you please repeat the question again?
So he's saying we have 2 containers containing 2 steel nails, containing water. Nails.
Okay, yeah, okay.
Each of them containing water. One is pumped with nitrogen and the other one is with oxygen,
Yes.
which will undergo higher corrosion rate once they are shorted, like once they are connected with the wire, and why it happens.
Okay, I suppose that you have a membrane in between, right? One side you have a iron or steel, other side you have this, okay? See, now this is where the interesting thing that comes into picture, right? Okay. Now you have one side, you have steel, or which is nitrogen. Another side you have let's say steel with oxygen there, right? Okay, and you have membrane in between. Now you are connecting these two with a steel wire, and one side you're passing oxygen there, other side you are passing the nitrogen here. Now let me first of all make it a little more simpler one now. Suppose I have a stainless steel. Okay, I have a stainless steel. Okay, if I have a stainless steel, and one case I pass nitrogen, in other case I pass oxygen here, then what happens? The one which is passing with oxygen will start passivating, right? And so the potential will start moving up. The one with the nitrogen does not passivate in the active region. That will remain in the, if I connect these two, the metal in the active region will start corroding more. Okay, because the potential difference is going to be more actually. Now, suppose I have, let's say, steel or maybe iron instead of stainless steel, and I am now bubbling with, let's say, with oxygen here and nitrogen here. Okay. Now, what do you think will happen? Now, you assume the first scenario, assume that the water pH is 8 or something like that. If the metal has the tendency to passivate, the one on the oxygen side will start passivating, okay, on side passivating and start corroding it off, right? Start corroding it off, okay? And passivating, so it will be, it will start passivating, the potential will start going up, huh? So the one on the nitrogen side will start corroding at all because of the galvanic coupling taking place. Suppose, assume that you are now, having the oxygen here, and you have, in this case, you have a steel there, and both are not really passivating at all. Okay, both are not really passivating at all. Now, what do you think will happen now? The one on the oxygen side, there is a more cathodic reaction. The potential starts moving up, right? Potential starts moving up. When the potential starts moving up, this starts corroding more because it's not passivating at all. Okay. Okay. When it starts moving up, and this side, it is not having nitrogen. If you join them together, what happens now? Assume that membrane does not give you any resistance to it. Now, the nitrogen side will also, will galvanically couple. Now, when you couple galvanically, both of them will finally have only one potential, right? Isn't it? Assume that the resistance of circuit is small. If both the metals have the same potential, the pH is same. Very interesting question you asked actually. Both of them should, in my view, corrode at the same rate. Assuming that the oxygen that is getting reduced does not form a passive film, pH does not change. Even though you're bubbling with oxygen here, the potential starts going up, will corrode more. But what happens now? Because the potential is going up, this side potential is lower, but then when you short it together, it will have the same potential, right? Now the corrosion rate depends upon the war voltage. The war voltage is same for both. And so the corrosion will be same because it's not passivating at all. If one is passivating, and if the war voltage is more, positive side, it'll, then corrosion rate will come down. Other side, it's not passivating, but you increase the war voltage, corrosion will increase. Because both of them are not passivating, in my view, both of them should have the same corrosion rate as long as the war voltage is the same, as long as the solution is going to be same. That means you'll find this guy will also now bring down his corrosion. Because this guy potential goes up because the potential comes down, right? So you'll find that both of them will undergo same corrosion rate. You can draw an Evans diagram and see what really happens. It's a very, very interesting question, actually. Yeah.
So as time is running out, we'll take the last question now.
Yes. They're very interesting. Very interesting questions people ask. Very amazing, actually. Yeah. Thank you. Yeah.
The hydroxide layer during cathodic protection is also a passive layer. Does this has to be chemically bonded species like oxides? And which type of chemical bonding is regarded as a stable passive layer?
Yeah, I see. The passive film is chemically bonded only. Because it's an oxide, no hydroxide, right? It's a passive film is formed. Of course, they come slightly different. For example, anodizing is different. Okay, this passive film is different. Yeah, there are some differences there. But yeah, this passive film is bonded chemically with metal. Okay. And but then the addition behavior of chromium oxide is different from addition behavior of iron oxide, actually. It could be different. Iron hydroxide may be much more, less adhesive, less resistance to corrosion, all like that takes place. But it's chemically bonded, no doubt.
Yes, sir. So that brings us to the end. we have answered all the questions. I mean, you have answered all the questions. Thank you.
No, yeah, everybody. So I think it's very nice. I'm very excited today. The kind of questions that you ask is amazing, and I'm very happy that your questions are very deeper questions. I would say. I do hope that people will take forward and understand the subject more deeply. Yeah, thank you very much. Thanks all of you for asking nice questions, and thanks Kirtika and thanks the Omkar also for this one. Thank you very much. Should we now close it?
Yes, sir.
Thank you. Thank you very much.
Thank you, sir.